you basically, how can you detect something at the nanoscale and know that it's actually the right size? I was telling them that we use different types of techniques to characterize down to the nanoscale, not like looking at it with your eyeball.
Okay, so you guys can hear me, right?
Yeah, we can hear you good, loud and clear.
Okay, good. So, well, let me talk about that maybe in depth, or tell you that it's not a simple answer. And maybe you might want to mute your microphone right now because I'm getting feedback.
Okay.
Okay. So anyhow, when you get any characterization techniques, I guess a good rule of thumb, this isn't true all the time, but true most of the time, if you use the wrong technique, you'll get a wrong answer. So it's kind of like getting a calculator and putting the wrong numbers in and hitting enter. You'll get the wrong answer. So there's usually a window that you could believe that a characterization tool is telling you the truth. Another thing is they all have a physics that the characterization tools operate on, per se, a physical principle. So they would look at, like we were talking about before, we were saying like optical response. So what we might be able to do with some materials is we look at their optical response. But the optical response for, say, if we would look at optical absorption, so we're going to say, I'm just going to make this up, but I just wanted the number to be real. So we're going to say, or not real, a number that you can correlate easily. So let's take the color green, because I have a green marker on my screen. And we're going to say that's 100 nanometers. And that's what gold looks like when it's 100 nanometers. Does that make sense to everybody? So you can shake your head and say yes. So gold at 100 nanometers will actually absorb green, and it looks green. It doesn't look gold. I don't know if that's true. I'm going to say that right now, but I know gold is green at some point. Maybe it's 70 nanometers or whatever, but we're going to say 100 because that's a nice even number. But if we take the gold and it's 100 nanometers and it's perfectly round, gold will do that and it'll look green. But if gold's 100 nanometers but is shaped like a triangle, it won't look green. So again, you have to even define what is 100 nanometers. Is it circular? Is it a square, like a cube? I mean, those things will make a difference. And then again, if we would hit the light from a certain angle, if it would be shaped like an egg and you hit a gold nanoparticle, it'll be a different color because the egg is not uniform, right? There's a long side and then a short side. It depends on what side the light is impinging on. So, oh my point here is sometimes that the characterization tools can get a little bit shady, but we do need characterization tools. And maybe another level of the answer here is, because I can't see the audience, but I assume that you're all young pups and you're 20 years old and you're ready to go at life. You don't have like gray hair like me. So I have gray hair and I can't see that good anymore because I get old, right? And your eyes aren't as well. But when you're young college age students and ready to tackle the world, you could probably see down to 30 microns. So that's about, a hair is about, on average, there's different diameter hair, right? But a hair is about 100 microns or so. So you can generally see around a third of a hair. And if you think about threading a needle, you can kind of see that that's true. So, you know, a micron is 10 to the minus 6, right? So that's what we're looking at. So we're looking at 30 times 10 to, 30 microns is a piece of dust or something we're able to see. Below that, we can't see, like a third of a hair. Does that make sense to everybody? I just wanted everybody to see something like that. So below that, we need things. A microscope is like times 1,000, a really good microscope. And we could have in our SEM times 300,000. So we can take an object and magnify its image in some sense in a scanning electron microscope, or a high-end one. Like ours, we do 300,000x all the time. So that gives us some additional range. But there's all kind of different tests. They work on absorption, they work on reflection, SEMs, X-rays. There's all kind of different things. So you can certainly study a lifetime of nanomaterial characterization. In our presentations, we might go over that. I don't know who's covering what, but you know, I certainly cover nano characterization for 3 credits in my courses that I teach here at Penn State. So is that a good answer for everybody? You generally see about the 30 microns, and after that, you need a machine to help you.
Everybody, you still want to ask your question? Come on. I think that answered several questions. Oh, I still see a hand. Come on up. Come on up. Come on.
Yeah, you gotta do things in life. I don't know who you are. I can't see you, but man, just do it.
I'm gonna turn the camera on. I don't know if Hartsoon turned it off because
Yeah, he did. Now I can see you. Yeah, I can see you now. Everybody's real tiny, but I can see you.
Go ahead.
All right, so a regular substance or element, they have some mechanical property and then physical property and then material property, and they tend to not change for the same elements. However, we do just learn that it's changed when we bring it into a nanoparticle. So when we bring it into a nanoscale, it changes, which is why it make it to be the periodic to be multi-dimension, because we can make different material out of that. So I wonder, does the physics still work the same when we do it under the nanoscale?
Well, that's a. And if you can turn the microphone off so it doesn't fade or rebound. So yeah, that's better, and it is better when you turn the microphone off, because I can hardly hear because it's so much feedback. But anyhow, yeah, what you said is brilliant, and I'm glad you learned this today. I mean, if you just learned this today at the nanoscale. So a good question is, why do they call nanotechnology? Because this is your field now, right? Or this is what you're spending your summer doing. And the rule of thumb is below 100 nanometers, all the materials behave differently. So gold doesn't look gold. It might look orange, blue, and red, depending on what its diameter is below 100 nanometers. So we're all good on that. Does that make sense? And that's especially true. But now if we look at gold, we can kind of model it something like, I don't know, like a porcupine or something with a bunch of quills on it. Does everybody know what a porcupine is? They have a bunch of quills or whatever, or like a cactus that has a bunch of quills on it. And those would be like the electron charge on the outer side, on the outer core. And if we would reflect back on the periodic table, we look at the columns. So we say that, column 8 has 8 electrons on the outer core. It's a noble gas. They don't react for nothing. They're really chemically inert per se. And then if we would go and look right next to it at column number 7 materials, we say, hey, they're basically crazy because they want to be group 8, so they'll do anything to get an electron. So when we look at that column, that's a family. So that column as a family, we're going to say, hey, those materials behave the same. They're all crazy. Does everybody see that? And we could look at other columns like group 4, and we say group 4 as we go down the column, because their communication set, I mean, their size is different, like the atomic diameter, but the thing that communicates is that's 4 electrons in column 4. So we say that they have the same familiarity, and they're roughly the same. They're like a same family. Does that make sense to everybody? Now, what we just defined in nanotechnology is we take an element and we break it down so its surface to volume ratio is unique, and we're going to have a lot of charge on the outside, so they behave differently than, like, whatever group gold is in. It's different than gold. It becomes more reactive. Its color changes. And I want you to know this. Let me make this point. When you change the color, you're going to change the biological response. You change the magnetic influence. You change the opticals. You change the mechanical. You change everything. So to answer your question, yeah, you get a new material in some senses. So what are we? We're like alchemists from the medieval days. In some senses, we can make gold behave like lead. And that was always, well, they always wanted lead to be gold back in the day, right? But those guys, they did things with materials, and they were like magic. And that's what alchemists did, like the magicians back in the day. But what I always tell my students and like, why are we valuable? We're valuable because we can make materials behave like other materials. And we do that according to their atomic assembly and also due to their diameter. And we're studying right now, I want to be a little bit more, I guess, detailed in the discussion. We can look at nanoparticles, right? And that's true. So I think that's what everybody has on their mind now is gold nanoparticles because Osama was talking about it, and that's fine. But we can also look at, we get nanoscale materials and we put like a nano film. It kind of looks like a sheet of paper. It's nano thickness, but the width and the length is like rather large. We can put a nano film on something like glasses. And when you put that on glasses, the nanofilm on the glasses, they don't reflect as much, or they're UV protected and all these other kind of things. But they're not nano, like that you can't see them or whatever. They're on your glasses and you can see through them, right? So we might do things like take carbon, assemble it in a particular way so that we get a diamond-like film on glasses. And diamond's transparent, but what's nice about diamond is it doesn't scratch. So if you want really good scratch-proof glasses, you put a diamond-like nano coating on it that's nano thick, but then it protects your glasses. And that's good for glasses, but we all know the more expensive glasses are, we lose them at restaurants, right? Or we drop them out of our pocket where we leave them on the beach. It might be a little bit more important because we keep track of things like binoculars or photography equipment a little bit more than losing our glasses. But if you ever wanted good binoculars or good photography equipment, you always want a diamond-like film on it. Does everybody see that? And then you might want those films on things like, and I'm not saying this explicitly, but wear items like piston rings or gears or whatever, we might want to put some kind of nano coatings on those to make them last longer. And we would do those things with like titanium nitride, which kind of looks gold. And we would put those things on like drill bits. I think I have one right here. Yes, I do. Here's a drill bit this is my cup where I put my pens. And let me get to the camera. Can you see this better? That's a drill bit and it looks gold. Well, there's powder on there because I was actually using it in the lab to drill things. But that titanium nitride is a wear coating.
Terry,
Yes.
we're not seeing, only thing we're seeing is your PowerPoint. We're not seeing your examples.
Oh, I'm sorry. Okay, let me stop the share. Okay, there you go. Now can you see me? Am I on? Okay, so I only see myself. There's like a little window on the side, and I see like 4 people. So, okay, here's glasses, as if you didn't know what glasses are. Because I was doing this. I was like moving them around. I want credit that I was moving them around. And you put these diamond-like films on here, right? So then when you clean them, they don't get scratched. Can everybody see? You want that. Because now it made your glass go up like $10 for that option, but they last twice as long. So if one company sells nano-coated glasses and another doesn't, then they should go out of business. I mean, you're at Walmart I bought Walmart glasses Saturday because I lost my sunglasses at Lowe's last week, so I had to go buy new ones. So I looked to see if they had scratch-proof stuff on it. Does everybody see that? I'd never buy a really good set of binoculars costs $1,000. That's true. Like good Swarovskis or Leicas. If you're a bird watcher, you don't have to buy them. But good binoculars are $1,000. Well, you want them not to scratch when you clean them. Does everybody see that? Because then you'd have to throw binoculars away like you're throwing away coffee cups, right? You're not going to do that. That's stupid. So that allows those things to last longer. So if you ever get good photography equipment, that's what you want. Now, what did I do I got all excited. Did I lose my drill bit that I was just holding up? Oh, my. I thought I put it back in my, oh, here it is. It fell back in this is my cup where I keep all my pens to grade and stuff like that. And you can see on here, I guess I can hold that up. Hopefully you can see. It's a gold colored drill bit. And if you go to Lowe's or Walmart or Home Depot and look at drill bits, they'll have black oxide coated ones. And that's for wear coating and lubricity. You'll also have these, and these are the better ones, these titanium nitride ones. And these will make the drill bit, they'll say that they last 3 to 10 times longer, and that's true. So when you put this coating on there, that might increase the cost by 20%. Now the drill bit lasts 3 times longer. So I'll do the math for you. You'd be really stupid to buy a regular drill bit because while this costs more, it's going to pay back more. Does that make sense? Because you don't have to replace it. It's going to last a lot longer. They also do this, you can see this in stores, with razor blades. So razor blades are ridiculously expensive, to shave with, right? So they make the gold colored ones and they last longer. You just go to, where you look at clippers to cut your hedges. They have gold colored ones and they last longer. So you kind of want to buy that, right? I mean, they're more expensive, but your pruning shears like to cut your trees last longer. Does everybody see that? So I hope that you guys know that you have the very good potential in nanotechnology to do things like solve cancer. But what you might do too is work for a company that makes lawnmower blades or something that last longer. Does everybody see that? And there's nothing wrong with that. I mean, if you make a razor blade that lasts twice as long, that's great. Does everybody see that? If you make a car tire that lasts 60,000 miles instead of 30,000, that's great. Does everybody see that? So that's what we do. We make a lot, and that picture that Osama showed before, nanotechnology is all over the place. And paint, like 80% of paint is titanium dioxide on the nanoscale. And I said before, gold can come as a round object or it can come as a triangle, right? We can make titanium dioxide. I'm just waving my hand so you get an idea. These are examples. Does everybody see that? But titanium dioxide could come as a circle, or we could make it as a triangle. The triangle one's good for UV. So now you make a paint that's real durable due to the circle ones, and you put some triangles in it, a different flavor of titanium dioxide, and the paint doesn't crack and it lasts forever. That's really good for cars. Does everybody see that? So nanotechnology is in all paint, and that's really, really important. And why paint's better today than it was 20 years ago? Because people know how to make the different size titanium dioxide and also how to put so much in the paint so that it has those attributes. So I'm not telling you anything that's like scientific or curing cancer. They have this written on the side of paint cans up at Lowe's. So go to Lowe's and Home Depot. It's on the side of paint cans. When you go to buy glasses at Walmart, you can find a pamphlet that talks about this stuff. Nanotechnology is all over the place. Is everybody good on that? They're really good questions, And the thing about answering these questions, let me tell you a story. You're not wasting your time. This is not messing around. This stuff's valuable. Does everybody see that? This isn't somebody's dream or going to be the future. This is today and yesterday. If you don't make good car tires, you're going out of business. You don't make good sunglasses, you're going out of business. This is where stuff is today. People expect drugs that are made with this, so the drugs are more effective. That's where we're at today. We can't go backwards. Does everybody see that? Everybody wants these things. Smartphones, not flip phones. Does everybody see that? Nobody's going backwards. Everybody's addicted to these things. I was surprised. I asked my students, I said, what about these $1,000 phones? And they're like, yeah, we'll pay it. And I'm like, you eat ramen noodles, but you'll buy a $1,000 phone. I like better noodles. I don't care about phones, but that's just me. I'm an old man. All right, so go ahead with your questions. Or laugh more at the old guy. All right, laugh all. I think it's funny. I laugh at myself. I got a mirror at home. I just got to laugh at myself mirror. Nothing wrong with that. How about it? Thanks for the questions.
Thank you.
I'm going to share the screen and start on vacuum, right? And what I did, I put more than enough notes because I knew we probably would ask questions and all that other stuff. So you can go further with the notes. It even says in the notes are the ones I submitted weeks ago. I gave you a lot more notes than is necessary for reference material. So, I'm going to try to go through this and cover as much as I can. So let me go to my share here, pull up my presentation again. Which one of my PowerPoint slides show? Well, I think it's this one. I don't know why I have two open. Yep, this is the one. So here's my presentation on vacuum, and this is what we're going to talk about today. So what I'd like to start out, well, here's my outline. So here's what I'm going to do. Really what I wanted to get through maybe is the first part and some of the pumps, but I have extra things in here, and we'll get done as much as I can. And then down at the bottom, the last thing is I gave additional notes that you would have them just in case you need them. And it's about vacuum hardware. And for some reason that seems to be, well, it's really, really important, right? But it's left out a lot of textbooks. So that's kind of strange that people in industry, they always ask me, like Boeing or whatever, these companies, they're like, do you teach the kids vacuum hardware, or do you show it to them? And because I guess it is lacking in books quite a bit, and I always say yes. So I put that in as an addendum, and I knew that we wouldn't be able to get to that today before we even had a lot of questions and whatnot, when the questions were real good. So that's fine. But I just wanted to make sure that you guys know that we have that. So why do we want to have vacuum, or why do we think that this is important? And it's because vacuum equals clean. So there's a quick word association for you. Vacuum is clean. Is everybody seeing that? So vacuum is clean. And why is that important? Because when we're making nanotechnology, generally for a lot of things, we make them on the scale or the dimension, at least in one dimension, like the sheet or a wire or maybe even a particle. We're making them on the dimensions of a virus. Does that make sense? And those things are really, really small. So we're looking at getting a number of atoms, like dozens of atoms or 100 atoms or something to make our product. So we need to have a dozen or 100 atoms that we want to have. Does everybody see that? So like in this room, or the room that you're in, if I tried to assemble something on the atomic scale that was 90 atoms of, just say, pure silicon, in your room that you're breathing everything, well, there's the breath. So you have oxygen, you have, whatever, water vapor coming out of your mouth, carbon dioxide, all these aspects of respiration. Does that make sense? And I saw in your video some people were eating a sandwich or something. So that now you have, whatever constituents, you can smell a sandwich or garlic or, ketchup or something. So if you can smell them, those atoms are floating around. So we want to do like 90 silicon atoms. Then all of a sudden we have some ketchup atoms in there and some carbon dioxide, and we really didn't get the thing we wanted to make. Does everybody see that? So why do we operate in a vacuum environment? It's because the environment that we're all sitting in is too chaotic. There's too much chemistry going on, especially water. Water's crazy because what is water? Water's hydrogen and oxygen. Does everybody remember that? H2O. So water's that, but when you look at chemistry homework, what are you always looking at as answers? Like hydrogen bonds, oxidation. Hydrogen and oxygen are movers and doers in chemistry, right? And if we're doing nanotechnology, we probably don't want to have the wild card or just this unknown water vapor to go in our nano product, like our transistor or sensor that we have in our cell phone, because then our sensor won't work. Does that make sense to everybody? That's just how it is. So why we have vacuum, we generally evacuate a chamber, then it's clean. And we know what's in there, which is nothing. Then we add in pure gas, and we know that it's pure. So then we can have the reactions that we want. Does that make sense to everybody? So I'll tell you a story, and it's a true story. Without vacuum, you can't make a cell phone. So don't let that scare you. People like fall. I'm looking at the camera expecting people to fall on the floor. So without vacuum, you can't have a cell phone. And where would a millennial be if you don't have a cell phone? Then you don't even exist. How about it? So that's a tragedy. So without vacuum, no cell phones, no internet. Cars wouldn't get 30 miles a gallon because they require sensors, like solid state sensors, etc. So without vacuum technology, the stuff we have today in 2019 is modern devices like GPSs and, razors that last twice as long, or drill bits, or any of those. We wouldn't have them. So that would be a sorry world. We would be back in the, the 1940s or something. So without, vacuum technology, the products that people buy generally, we wouldn't have them. Like all of what's in Best Buy, the store Best Buy, it wouldn't exist, right? Certain sections of Walmart wouldn't exist because we wouldn't have a TV, like flat panel display TVs. We wouldn't have them. Vacuum also equals safe. So when we work with materials, some of the materials we work with are like especially insane. So materials that we work with a lot are materials that they used to use to kill people with in World War I. They're like banned by Geneva Convention. So a really good one that they used to kill people with in World War I, like gases on the battlefield in 1914, right? They used to use like phosgene, like this phosphorus-based material, and it would cause these miserable deaths and suffering to people. Does everybody see that? And mustard gas and all these other things that they used to use in war. And we use that to make the inside of your cell phone is made out of those things. So when you dope something, you use phosphorus, like N and P type, right? So I hope you guys know about semiconductors, at least a little bit have heard of that. So a really good N-type dopant is phosphine, which is a really close cousin of phosgene. And phosphine will kill you like now. Does everybody see that? So we really just can't have phosphine in the room because everybody would be dead, and that's not much of a workplace. So we have to have a contained environment, and we mix silicon and phosphine together to get like N-type materials. Does that make sense to everybody? So we work with stuff that's rather hazardous in a lot of aspects. So we worked in a protected environment, a controlled protected environment. That's why we have vacuum. So simply stated, you know, once again, if we don't have vacuum, there is no such thing as like the information age or semiconductors for the most part, because we just can't process materials at that level. So this is real environmentally conscious, right? So that it's safe. We can do a reaction. If there's anything left over, we put them through scrubbers, you know, so they don't chemically interact with the environment, and everything's pretty safe, right? So there's a lot of equipment that's based on vacuum technology. So again, when I talk to businesses, like the big businesses that were likely to hire you, like semiconductor companies or sensor companies, aerospace companies, medical companies, pharmaceutical companies, they always ask if I teach vacuum, right? And the reason why I'm invited speaker here today is because my area is vacuum technology, right? So that's really, really important. So these are really important for a lot of processing machinery that we would use in nanotechnology. So things like sputtering tools, metal evaporators, thermal evaporators, plasma-based tools, whether they deposit or whether they remove material, their foundation of them in those systems, which we'll look at today briefly, is based on vacuum pumps. So they're really, really good. So this, and also characterization tools. So the question before was characterization tools. What do we need to see things that are as big as a virus? And we need things like the scanning electron microscope. And basically you can't have one unless it has vacuum pumps on it. Does everybody see that? So there's all types of characterization equipment that requires vacuum as part of its infrastructure. So vacuum is no joke. Vacuum is foundational. So I wanted to make sure that you see that. So vacuum is the remover of gas molecules, which is air, moisture, and gas residues in a closed container to achieve a pressure less than atmosphere. So that's what we do. So we take a closed chamber. Often these chambers are like big that you can put your arms around. Does that make sense? Like big as a laundry basket, big as an apartment refrigerator, maybe big as a microwave oven. Does everybody got a concept? And we generally process materials that look like paper plates that you would eat pizza on, or pizza, right? So that's about as big as the material that we would deposit or remove or work with a lot of times. And machines would reflect that. So those are generally the size. We can also have machines that are as big as a room. And they're nano machines, and they use vacuum, and they deposit like metal coatings on things like windows that they would have on big apartment buildings or whatever. So those are exceptions to that. But generally a machine is something you can put your arms around. Does everybody see? And those are the machines you'll be seeing in the nanofabs throughout your experience here in the summer. So without vacuum, we wouldn't have many nanofabrication processes, and we wouldn't have a lot of characterization process. So for the most part, just as like a logical statement, I'm just saying this, if you don't have the concept of vacuum, we really don't have the year 2019 as we see it. And it's so important. That slide that Osama showed you with all those devices on there and nanos and, you know, car tires are nanotechnology, right? It doesn't have to be that technically impressive. Like the rubber in car tires is carbon black, and those are nano-sized carbons, you know, elements, and they have to be kept to a certain size, and then your car tires last 2 or 3 times as long as they did 30 years ago. Does everybody see that? So this has a lot to do with basketball shoes, car tires, and paint that's on pencils, right? So this has a lot to do with everything. So vacuum is integral to getting this done. So these are the key things in technology, the properties of gases. And I'm sure that, you selected for this program, you have to have a certain technical background. So you should have had EE 101, Chem 101, Bio 101 kind of stuff, Physics 101 or Physics 1 and 2. And these are the standard things that you would see in a lot of those courses because it's so important. They talk about gas properties in chemistry. They talk about it in physics. They talk about it in materials, right? So these are the standard ones. So this is the roles of gases, and I won't bore you with it, but everybody can read that quickly and know this is what we're talking about. So, and maybe a question that's not on this list is, what are gases to me and you, and why are we talking about it in nanotechnology? A really good way to build things on nano is add a gas atom. Says everybody see this as a gas atom? Add one gas atom to another gas atom. That's hard to do in a solid, but in the gas form, that's easier to do. Does that make sense? I'm just saying, when we're making things that are as big as a virus, probably a real good raw material is atoms, not liquids, not solids, but individual atoms or individual molecules. And those guys come really good in the gas phase. Does that make sense? So gas is probably a very, very appropriate material to be used in a lot, not all, but a lot of nanotechnology. Does that make sense to everybody? So gas, like all the semiconductor companies have insane contracts for gas. Does everybody see that? Their production is basically, let's take a majority of the elements that are in your cell phone were at one time a gas. Is everybody in? There could be solid metals and stuff like that. But the gas phase, especially for like silicon and stuff like that, that's just how everybody rolls. So that's why vacuum's important, and that's why gases are important. And then we want to look at a concept called like the mean free path, and that's the average distance between gas molecules. And in a room, it's so small I can't even describe it. It's like billionths of a centimeter, and that's how close gas is. And who knows what a billionth of a centimeter is, because you can't even understand that. The number's so crazy, it's incomprehensible. But there is a formula. If we take the mean free path, we can take a number like 5 times 10 to the minus 3 and divide by the pressure and torr, and that'll give us the distance. And typical distances that we would like to have is centimeters or inches, and then probably a really good one for a lot of processes, we want to have meters. So we want to have a pressure in torr that's relatively low, and torr is a standard pressure. At atmosphere, it was fixed or invented by an Italian gentleman named Torricelli, I think is his name, and he invented that, and he said, atmospheric pressure, a nominal number like at sea level, is 760 torr. So we're going to talk about that, but I wanted you to know that sea level atmospheric pressure, like your classroom, is probably around 760 torr, maybe 750 torr, something like that. But that's standard pressure, is that. And we like to take that 760 and divide it by 1,000,000 or so. And we like to run it 10 to the minus 3 torr or something like that, 10 to the minus 6 torr, maybe dividing it by millions of times. And that's how much gas we would like to have in a vessel. So the pressure, like to define pressure in a vacuum, it's the force exerted over a unit area. So again, you've had this in your physics courses a bunch of times. I don't want to bore you too much, but this reduced pressure equals the chance of reduced collisions of the gas molecules as they rebond within this closed vessel. Does that make sense? And we could look at this, the theory of pressure is if we take the gas molecules as an impinging force and the area of the enclosure, we can say the pressure is the force divided by the area. And that's certainly true. And maybe another picture that will help us look at this is, we don't have, on this wall in the first picture on the upper left-hand side, says that we don't have any pressure on the wall because we didn't have a collision event yet. But once we have the collision, and we had one molecule or one atom, we would have a pressure, and that arrow represents a vector value, and we're going to say that's a vector value of 1. So one collision is going to give us that magnitude of that area. And so that's a very low pressure because there's only like one guy inside the chamber, right? One atom. But if we look at 2 atoms in that chamber, then we would say the pressure is double that. Does everybody see the arrows twice the size? So that's a vector representation of that. And when there's even more gas in there, then that pressure is even better. So at atmosphere, you know, impinging on the wall in your classroom or on your desk is the amount of atoms that would give us 760 torr. I hope that makes a lot of sense to you. So pressure is that entity. So atmospheric pressure, when we look at it, it's actually the sum total or the integration of different gases. And these gases, this is a nominal value. So this is different if you're in the middle of a cornfield, or if you're near an ocean, or if you're up the top of the Colorado mountains. Does everybody see that? But as a norm, just in chemistry, people like to have this. So they say at sea level, we get about 78% nitrogen, about 21% oxygen, maybe 1% or so of argon, and then small amounts of these other guys. Does that make sense? And then not listed is water. And that's crazy. We talked about that before. And it's crazy because we know when we do our homework, we're always circling hydrogen reactions and hydrogen bonds and things that are done with hydrogen, right? And in biology, ATP to ADP and things like that. And then oxygen, oxidative states. I mean, you know, oxygen's quite the player in chemistry homework. How about it, guys? So anyhow, those things are important. So it's kind of funny on this list, they don't even mention water vapor. And probably one of the reasons they don't mention is it changes so much. And again, it changes whether you're out in the desert in Arizona. There's hardly any, per se, humidity, water vapor out there most times of the year. And then if you're in a place that's near rivers and real hot, maybe down south in a swamp in Alabama or something, the humidity there is probably 100% all the time. I know I'm originally from, you can probably tell my crazy accent, right? I'm from Pittsburgh. So in Pittsburgh, humidity is always tremendously high because we have a bunch of rivers there, you know, and the, you know, just how the mountains are, et cetera, like that. So humidity in Pittsburgh in the summer always is, you know, 70, 80%. It's really hot and muggy down there, hazy quite a bit all the time because of the water value. So that's a lot different than in Phoenix, right? So Pittsburgh to Phoenix, that number is going to change quite a bit, and it's an important number. We can't have that variable in nanotechnology because we always want to assemble like 90 atoms or something like that and make our nano device or nanoscale things. We can't just have all of a sudden the wild card of water in there. Does that make sense? So one of the big reasons, like our reason, I would say certainly our reason that we have vacuum chambers, it's actually make sure we pump all the water out and we get the 0% water, because then we can have a controlled reaction. Does that make sense to you guys? If you're in different parts of the country or whatever and the water level changes, then your nano product will change. So we don't allow that to happen. We operate in vacuum chambers. We use vacuum pumps to get rid of all the water at 5 times 10 to the minus 4 torr. That's when the water all peels off for the most part, statistically. And then that means that our product is going to have very little contribution of hydrogen or oxygen. Wild card contribution, right? Unknown contribution. So then at that point, we could probably index the appropriate amount of hydrogen or oxygen if it was necessary for our product. Is everybody good on that? So here's nominal values of gas. So again, if we total up the whole torr, it comes out to 760. And nitrogen accounts for, out of 760, it accounts for 593 of that. Oxygen is 159 out of this nominal, by name only is what nominal means, 760 torr. And then argon's, you know, 7 torr out of the 760, right, nominal value. And as it goes down the scale. Does everybody see that? So you really don't have that much hydrogen, per se, in a cubic foot. Is everybody seeing that? Or helium or any of that other stuff. So that's a nominal, again, by name only. That's a standard breakdown of gas you could probably find in most chemistry handbooks. So when we look at atmosphere or vacuum, vacuum is the essence of no atmosphere. Does everybody see that? So if I would say to take atmosphere and have half of the gas in a chamber, then I would take 760 and divide it by 2. So that's 350, so it's 380. Does everybody see that? So if I had 380 torr, it would be roughly half of the gas compared to atmosphere. Does everybody see that? I probably want to divide that again and again and again and again, and I probably want to have 1,000,000 times less of the residual air inside a chamber. 1,000,000 times less, or even 10,000,000 times less. That's kind of crazy. And then there's different ranges that you should know about in vacuum, and then these ranges are from atmosphere to 10 to the -3. That would be the low vacuum range. The high vacuum range is defined as, in physics and in material engineering, as between 10 to the -3 and 10 to the -6. And below 10 to the -6, we're going to call ultra high vacuum. So specifically, we kind of have like ranges. Does everybody see that? And you might have ranges in your own life, like how fast is a car going? You know, like in a school zone or inside a city, you want cars to be less than 25 miles an hour, or like in a city and, you know, in a crowded area like in town, you don't have cars going like 80 miles an hour on a street inside a city, right? You have them go like 35 or something like that. So there's like zones, right? And on a highway, you don't want a car going 35 miles an hour. You want it to go like 70 miles an hour. Does everybody see that? So there's different ranges of like acceptable speed that you would have in cars, right? Just that. There's actually ranges of vacuum, so that analogy holds true. So there's things that are appropriate in vacuum, just like there's things that are appropriate when you drive a car. Does everybody see that? So that might sound strange. The car thing I don't think sounds strange to you, but the vacuum thing might be a little bit new to you, because, you know, naturally you're sitting in this class because you don't know this stuff. So you need somebody with a crazy accent and a big furry mustache to tell you these things. So here's the vacuum ranges. Like I said before, the rough vacuum is from atmosphere, like 760 torr, down to 10 to the -3 torr. So what does that mean? Let me get let me get a pen. So I'm going to draw a line. Let me see if I could do that. So I'm going to draw a line down here. Does everybody see that? That's as straight as a line I can draw. It's really terrible, isn't it? That sucks. So at atmosphere, we're going to have something like, my numbers are going to be even worse. Oh, that ain't turning out too bad. I'm actually, see how bad that is, and I'm proud of that. So that's how my life stacks up. So this is right in this level here, and I put the capital T for Mr. Torricelli, right? That's 760 torr, that's atmosphere. If I do that again, and then right here, I divide 760 by 760, I'm at 1 torr. Does everybody see that? And that's around 1,000. 760, 1,000, between me and you, they're the same. Does everybody see that? Then if I take 1 torr and I divide it by 1,000 again, I get 10 to the -3. I'm surprised I could draw so well with this mouse. It might look really terrible, but for me, that's good. So then I get 10 to the -3. Does everybody see that? And then I might divide that again by 1,000, and I get 10 to the -6 torr. And then we even have machines that operate on 10, and it's just by a factor of 1,000, so it's easy to see and do on gauges. -9 torr. And that's kind of crazy, right? Let me finish that 9 for you. So that's good. So we take atmosphere and we divide it by 760, around 1,000. Does everybody see that? So 1 torr to me is like really high. And standard gauges always go to millitorr. So I take this is like a piece of pizza. I take a piece of pizza and I divide it by 760. And somebody at a party, you know, a frat party or college party, walks up to you and says, you paid a $10 cover fee to get into this party. I'm now going to offer you 1/760th of a pizza. That ain't much pizza. Does everybody see that? And then that's how small it is at 1 torr. In material engineering, we take that number and we divide it by 1,000. So we take this little piece of pizza, 1/760th, and we divide that by 1,000. So there's hardly anything. Does everybody see that? And then to be really good, most stuff is made, in some senses, the vacuum system went down to, or could go down to, 10 to the minus 6. So we're taking a thing, divide by 1,000, take that, divide by 1,000, take that, divide by 1,000 again. So how much gas do you have in a chamber at 10 to the minus 6? The answer is almost 0. Does everybody see that? That is crazy. Remember, the first statement is vacuum equals clean. Is everybody hip to that? So we're all good? So what's 10 to the minus 6? Crazy clean. Does everybody get that? Crazy clean. So that's where we do our material. That's where we do our work. Does everybody see that? So like, I'm a guy that does nanotechnology. I expect to hear things like 10 to the minus 6 in my daily life, because that's like hearing a car going 70 miles an hour. Does everybody see that? It's just a standard thing. You probably have never heard of vacuum ranges or torr or whatever, but 10 to the minus 3 torr, 10 to the minus 6 torr, standard stuff. Does everybody see that? So you'll see that when you're doing your research, or if you're working with vacuum equipment, that'll come up. Does everybody see? So now I guess I have to do something like maybe erase these lines. I don't know. My computer's hung up. Oh my, don't tell me I have to erase everything. I think I have to erase everything before I can go forward. Hey, I hate computers. I kind of like my cell phone. A little bit. I don't like to pay the cell phone bill a lot. I don't like to buy a new cell phone. They're so expensive. They're pretty handy. Listen to Pandora a lot in my truck. So that's free. Well, not free. I pay the big bill. Now can I go? Whoa, I got to go forward. There we are in technology. I can shift the slide. So here's the pressure at atmosphere. Then a common thing is 10 to the minus 3. Does everybody see that? Numbers you probably didn't hear before my talk today. And then here's a big number, 10 to the minus 9, and that was on my chart. So the number of molecules per cubic centimeter. And you guys know how big a cubic centimeter is. It's like a couple few peanut M&Ms, right? It's like big as a sugar cube, right? So if you have sugar cube and like tea and put sugar cubes in there and stuff, it's that big, right? Or you feed horses, you put a sugar cube in your hand, hold it flat, the horse licks the sugar cube. So do that this summer. That's good. So there's 10 to the 19 at atmosphere. I don't even know what that means, because 10 to the 19 is so big, and I'm so stupid, I don't even know what that means. 10 to the 13 at millitorr. That's so crazy, I don't even know what that means. At 10 to the minus 9, it's like 10 million. I kind of might understand what that means, because that's like what baseball players get paid, right? So I kind of got that. Here's that mean free path. And what the mean free path is, let me get my things up here. These are actually bottle caps from water bottles. But now they're tax deductible learning objects. Does everybody see that? So say yes, so I can deduct these on whole cases of water on my taxes next year. So here's my water, or my atoms. When they're at atmosphere, they're so close together, they're touching, and I can't even envision it because it's a millionth of a centimeter. So they're touching. Does everybody see that? But at 10 to the minus 3, they're actually 5 centimeters apart, which is 2 inches. So that makes sense to me, because the average distance that an atom in the chamber before it hits into it, it's about 2 inches. Does everybody see that? That's the mean free path. That's that lambda that I presented earlier in the presentation. Then if we go to 10 to the minus 9 torr, which is really far vacuum, then it's 48 kilometers. And 48 kilometers is something like 30 miles. Does everybody see that? I'm going to guess in that room that you guys are sitting in there down at NSU, nobody's ever walked 30 miles in a day, because it's going to take you all day to walk that far, and you'll probably have blisters. You know, that's a really far hoof. Does everybody see that? If you were in the military, you might have done it, but that was a bad day for you in the military, I'll tell you, because that's really, really far. I know, like in the Civil War, guys walk that far. They typically sometimes would walk 20 miles in a day, which is insane because they had to carry all their equipment. Those guys were really tough, But 30 miles is further than you are willing to walk, I would say, on average. I'm not insulting anybody. I'll tell you, I don't want to walk it. That's for sure. And then let's reflect on this. What does that mean? Well, it means that we're not really super walkers. But let's reflect on maybe something that's maybe more important than criticizing our physical ability to walk really far. How big is a chamber? A chamber is big like this, right? It's big as a laundry basket, big as a microwave oven, big as an apartment refrigerator. Does everybody see that? So if you have a chamber and it's as big as a microwave, then you're probably going to have gas touching each other because it's bigger than 2 inches. Does everybody see that? But if your mean free path is 48 kilometers, the gas in there is probably ever going to hit each other, and it's really, really clean. Does everybody see that? So the mean free path is a statistical number, and it's hard to get your head around, but it's a distance number. So this previous table gives us some insight for system design and contamination issues. The mean free path is also critical to understanding dissociation in plasma. We'll talk about that later, but let's look at the thermal evaporator. So I want to give you your first machine in nanotechnology. Is everybody focusing? So this is an important time. We're going to look at our first machine. This is called a thermal evaporator. What we want to do with this machine is we want to make a mirror. So a mirror like you have when for, I guess, the guys, right? Me, I shave, right? So I need a mirror so I can shave and stuff, comb my hair, whatever, typical things, right? So you need a mirror in a car, like a rear view mirror when you're backing up, you don't hit somebody, right? So we want to make a rear view mirror for a car. So we want to make a rear view mirror for inside our Toyota truck, right? And what we would do is up top, this is our substrate. And my substrate's a piece of glass. And from the factory, I got a piece of glass, but it's not much of a mirror because we can see through it. Does everybody see? So to have a mirror, what we have on a piece of glass is we put a thin metal coating. And that metal coating is going to reflect the light. And that gives us our mirror. So a mirror is glass with a nano coating of metal on there. Does everybody buy that? That's what we want to do. So here's my thermal evaporator. We have different gauges on here. This CTM is called a crystal thickness monitor. It's going to tell us the thickness of the metal. It also tells us the rate of deposition, which is important. And here's my pumps. I have a low vacuum mechanical pump, which pumps to 10 to the minus 3. We also have, it's a helper pump to this turbo pump, because the turbo pump can't operate unless it's at high vacuum range below 10 to the minus 3 torr. So this is a helper pump, and it actually pumps on the back end of this turbo pump, and it roughed down the chamber to 10 to the minus 3 on this side. Then we also have here is a shutter, and what the shutter is going to do is act as a filter for our material, because our material, when we first start, the material is going to be contaminated. So what we do with the shutter is the material that's contaminated, we're going to get the contaminated material and stop it, and it lands on the shutter. When the material is in steady state after we burn it up for a while, then it's going to become pure. We're going to move the shutter, and then the pure metal is going to go on a substrate. The tungsten filament, tungsten melts at 3,600 degrees C, and times F, that's 1.8 plus 32. We don't have time for that. Times 2 is a better number than the 1.8 plus 32 because it's quicker in your head. So it's like 7,000 degrees Fahrenheit. That's insane. Does everybody see that? 7,000 degrees Fahrenheit is a big number because we cook chicken and brownies and stuff like that in the oven, or pizza, at 350 degrees. Does everybody see that? So 7,000 degrees is a lot more than 350, and that's where we would cook most things in the oven, like, chicken and pizza and stuff like that. Does everybody see what temperature is? And I'm surprised people don't cook no more. What's wrong with you? Cook at home. Cooking is great, man, because you make food and then you can eat it. Cooking's a great hobby. So if you don't learn anything else in nanotechnology here over the summer, learned that you should cook and cook really good homemade pizzas and brownies and stuff like that. So there's a tip for you, like a pop-up window of wisdom. So learn how to cook. And we're cookers here in material engineering. I think the things are very similar. So anyhow, here's my machine. Does everybody see? So here's my pumps that we're reviewing in the next chapters, right? But I'm giving you a preview so we see where we're going. So here's my machine. I want to put metal on top of my piece of glass. Does everybody understand that? So you might not know this, but on my tungsten filament, it melts at such a high temperature, I can put another metal on there and use that as like a boat or like a spoon or like a pot. And you know how you get a pot, you boil water on the stove and you make water steam or water vapor? You might have never thought of this, but in a vacuum, what you could do is take a tungsten pot that's shown by this filament right here. I can take this tungsten pot, and what I can do is I can put aluminum on it. So instead of boiling water, I put aluminum pellets on there. And the aluminum pellets look like those jimmies or whatever they put on top of donuts, like pencil lead, all chopped up, like they put on birthday cakes, right? So they can put aluminum pellets in there inside this thing that looks like a spoon. And then under vacuum, what I do is I heat it up to like 600 degrees C, and that aluminum will actually vaporize to aluminum steam. Isn't that crazy? Aluminum, solid aluminum, could become a vapor like paint. So now I have aluminum paint. Does everybody see that? Now the aluminum paint straight, let me get that pen again. Where the heck is that? Did I tell you I don't like computers? Now I can't find the pens. Whoop. Click the screen, went crazy. No wonder I don't like computers. Oh, here's my annotate. So here's my draw. Let me get a line in here. So my aluminum's going to go like this and spray like a cone. Does everybody see that? So in here is my cone of aluminum spraying up. So when I initially start so I have my aluminum pellets in here, like little jimmies, right? And then I put heat on this, and I heat it up so much that my aluminum turns into a spray, like spray paint. My aluminum always has a coat on it, like aluminum oxide. Does everybody see that? So you don't touch aluminum. Aluminum always has a skin of oxidation on it because at atmosphere, it just gets like a rust. So aluminum rust is aluminum oxide. Did you guys know that? So I'm going to ask you a question, and I want an answer. So somebody go to the microphone. Somebody volunteer to go to the microphone. And I'm going to ask you to tell me what you think a metal is. So somebody go up there. There's a brave soul. Go up and tell me what you think metals do, or what their attributes are. Describe metals. You got to turn it on. And I see the icon. So it's turned on. Go ahead. So what's a metal?
A metal is an element or a material that is a good conductor of heat and electricity.
Yes, that's excellent, because we can model metal as an infinite sea of electrons, because they have like ion cores like magnesium, and then a bunch of electrons rotating around them. So a quick model for most physicists, a very valid model, is we can say metals are an infinite sea of electrons, therefore they conduct heat rather well and electricity rather well. That's certainly true. What else about metal, just in general? Like, you have a piece of metal, what can you do with it?
Yeah, go ahead, say it.
They're malleable.
Yeah, they're malleable, which means we can bend them. Does everybody see that? They're real bendable. Another one, go ahead. When you look at a metal, what does it look like?
Saying reflective and shiny.
It's reflective and shiny, that's right, because a photon is actually an electron. Does everybody get that from the duality principle? So it's already an infinite bucket of electrons. It doesn't need a photon. They just bounce off because it's already a full bucket. Does everybody see that? So photons and electrons, the duality principle, that's like an Einstein thing. That's cool. And that means that they're shiny. So metals are shiny. Metals are ductile and malleable. Metals conduct electricity rather well. Does everybody see that? And when you bend them, they don't break. And you could probably bend them back. Does everybody see that? I think that's a good job of what a metal is. And we're going to say aluminum is like that. Does everybody see? Aluminum is a metal, and we're going to say aluminum meets those constraints. So now you did your good deed. Let's make somebody else in the hot box. Somebody else take this gentleman's place. And you know what you have to do? You just have to go up and don't be afraid if you don't know the answer, because you wouldn't be here unless you didn't know the answer. So be brave. Somebody be brave. There's a brave guy. Hello, brave sir. So now I'm going to ask you questions and put you on the spot, embarrass you. You'll be so embarrassed you're going to puke. So let's go ahead and make this guy puke, because that's what I got up today to do. I wanted to be so rude. I want the people to puke. So let me ask you this. There's metal is a type of material. There's also another material called a ceramic. A ceramic. So let's say the attributes or the properties of ceramics and compare them to metals. So tell me what you know about ceramics, or people in the audience can help you, like it's the Price is Right show. Ceramic.
They can withstand a lot of heat, like they hold heat well.
Yeah, so they don't conduct heat. They're insulators, both electrically and heat-wise. So how different is a ceramic than a metal? In conduction of heat and electricity, 100% different. They're apples and oranges, ones and zeros, salt or sweet and hot. Does everybody see that? They're 100% different. Okay, good. Let's look at their mechanical properties. So how does a ceramic bend?
It cracks.
It cracks. Metals don't crack, they bend. So again, a ceramic is exactly opposite of a metal. Hey, how about the optical properties of a ceramic? Or ceramics, when you look at things like sand, is sand real shiny?
No.
No. And metals are soft. You can scratch them usually, right? Can you scratch things that are ceramics? No, they actually use ceramics to sharpen knives. You know what a good ceramic is? Does anybody know what when you go to Lowe's or Home Depot or Walmart and you buy sandpaper, when you look at the back of the sandpaper, the paper part, it'll tell you what it's made out of. Does anybody know what the most popular thing to make sandpaper out of is? The most abrasive material. Does anybody know?
No.
It's actually aluminum oxide, Al2O3. So let's look at my experiment here, my machine. Let's go back to so you're done. Thank you very much, brave sir. Everybody was brave that answered, and it didn't hurt. Nobody got hurt in that. It's like movies. No animals were hurt in this, making this movie. No students were hurt in my presentations. Does everybody see that? And in fact, all my students should laugh in my presentations. And you guys should take life pretty seriously, but you should also laugh. I'll send that along for free. So anyhow, here we go, boys and girls. My aluminum here, if I evaporate aluminum and it goes a centimeter and it hits into oxygen, and it goes another centimeter and hits into oxygen, and it goes another centimeter and hits into oxygen, and it's going to go this far. When it lands on my mirror, it's not going to be aluminum, pure aluminum. It's going to be aluminum oxide. Does everybody see that? So if I have a bad vapor in here and a bad mean free path, like a poor mean free path, we know my mean free path is going to be like a meter. But if my mean free path is centimeters, that means my aluminum is going to statistically run into like oxygen and hydrogen and nitrogen, all those things that we have. And what's going to land on my glass is aluminum plus a bunch of other junk, like aluminum oxide. Does everybody see that? And so my mirror is going to be dull. And it's not going to be a good mirror. Does everybody see that? So let me go back to that slide. Let me show you this. I think I have to X out of here and then I can go backwards. Oh, I got to erase this. Hold on a second. Oh my. Oh, I can't find the annotate. There we go. So now I got to get my eraser because this thing stays on all the slides, which is crazy. So I'm going to go back in the slides to show you this. We have these mean free paths. Does everybody see? So with just a mechanical pump, which we're going to learn about in a little bit, we would only have 10 to the minus 3. So the mean free path is 5 centimeters. So every 2 inches, it would hit into some oxygen, the aluminum. And when it lands on the mirror, it's going to be like aluminum oxide, like sand. And it's going to be terrible. It's not going to be a good mirror. It's going to be dull mirror. Does everybody see that? But if I had my chamber at 10 to the minus 6 or 10 to the minus 9, it's probably going to be in meters. 10 to the minus 6 is going to be like 100 meters. It's not on this chart, but I'll tell you that answer. So if I was able to, this turbo pump makes this machine go 10 to the minus 6. Statistically, even though this distance is only like a 1 meter, the average distance the aluminum is going to go is 100 meters before it runs into oxygen. So if I pump what does 10 to the minus 6 torr mean? 10 to the minus 6 torr means this machine is so clean that I can transfer that aluminum from the filament right here to the substrate, and my aluminum is going to remain pure. And I'm going to make a really shiny mirror. Does everybody see that? So I told you before in my presentation, and this is a takeaway message, vacuum equals clean. If I don't have a real good vacuum level, my material's contaminated by things like oxygen and nitrogen, hydrogen, all that other water. Does everybody see? So why do we want vacuum? So we can make like pure mirrors. Do we want to just make mirrors? No. We want to make parts for like prosthetic hips. Does everybody see that? We want to make parts like artificial teeth that go into your jaw. We want to make parts like coatings on them, like heart stents that go inside your heart, like a spring that opens up your arteries. And if they're not pure, they're going to have the reaction that you don't want, and it's going to kill you. Does everybody see that? So we need vacuum to make like biomedical parts. So why do biomedical companies care that I teach vacuum? Because that's what they need to make their parts. Does everybody see that? This is how we make pure drugs. This is how we make pure cell phone parts that work reliably. Does that make sense? You know, so the purity level to make nanotechnology, some, not all, but some processes really require vacuum. Does everybody understand that? I want you to leave this presentation and say, vacuum is important. And what my name's Ter, T-E-R, right? So what Ter talked about today was like really not silly. It was like I could see the money. I could see this is important. I could see I don't own a cell phone, or people can't make cell phones unless we have vacuum technology. Vacuum is, there's many cornerstones in nanotechnology. Vacuum is one of these cornerstones that are tremendously important to a lot of processing of material, not everyone, but a lot of the material processing that we do in nanotechnology is 100% reliant on understanding and being able to use vacuum processing. Does everybody understand that? Vacuum processing isn't something that you will not ever hear again. If you're in material processing, vacuum is a standard. Does everybody see that? It's like wood to a carpenter. Does everybody see how just like wood to a carpenter? It's just given. Vacuum to material processing on a nanoscale, just like wood to a carpenter. Does everybody see that? It's like hammers and nails. You just have to have it. So vacuum, while it might be like crazy, you never heard of it before, that's why you came to this summer course, is to hear these things that a small percentage of the population knows about, but this small percentage of the population, people that actually do know how to make nano products, they impact people greatly. I don't think I'd want to go into a hospital unless there was nanotechnology today. Certainly your chance of surviving cancer, etc., is tremendously greater now that we have nanotechnology than it was before the dawn of nanotechnology. That's true. That is very true. Worldwide, this is interesting. Between now and between the year 2000 and today, the relative amount of poor people on the planet has gone in half. Wealth has doubled. And this is for very, very poor, destitute people. These are numbers from the United Nations. So the amount of people that have benefited from advancements in science in the last 20 years, it made the planet literally twice as rich. And there's half, the level of being poor has doubled. And that's phenomenal. This means a lot less people starve to death on this planet. And that tracks greatly and has a lot of contribution from the ability of people to be smarter and to use things better. Does everybody see that? Like technology. And when we have technology like computers and stuff, we can grow more corn because we can plan things out or look at, study corn for all kind of reasons to make it more blight resistance, etc. So nanotechnology has so much impact on society, it's insane. But people don't talk about it because it's so insane. Does everybody see that? But it's true. I'm not here to, this is just it, right? I'm ready to retire, but I'm passing this along. This is good stuff. This is good. I'm proud that I did this for a living. It's a really good thing. So now that I retire, you guys have to know this stuff and make artificial knees because I need them. You have to make heart stents because I need them. And you have to pay into Social Security because I need that too. So I'm passing it along to you guys. Does everybody see that? So this is system design. So when we look at system, the film here in our example, the film will react if we're at like 10 to the minus 3. We probably don't have very good films. They're probably junky. So we would make things like watch bands or Chevy symbols like plastic and coat it with chrome. That's good enough, 10 to the minus 3. But if we wanted to have things that are really super pure, we would probably go to 10 to the minus 6. And those things are specifically, and again, I'm waving my hands around a bit, but I'm saying the world that we live in requires, for the most part, the ability to do vacuum at 10 to the minus 6 level, and that'll give us maybe the majority of the parts that are inside your cell phone. Does everybody see that? And I hope you guys know there is not millions, but billions of transistors in your cell phone. And we couldn't make things as big as a virus unless we had it so pure, vacuum equals clean, we couldn't make these billions of transistors. So I hope that these points are, light bulbs are coming on in your head, that vacuum's important, or we wouldn't have cell phones. Not that cell phones are that important, but to have communication and all that other stuff is simply revolutionary. And I think most people today, on a university scale or people that are moderately intelligent, they can make statements that, the advent of things like YouTube are as important to society as the invention of the printing press. That's true. You guys live in a new age, just like when people started to read, or we came out of the medieval days. Now we're in the information age. It's just like it's a revolution, like Renaissance, the Renaissance age, or when they made the U.S. Constitution. They made the Bill of Rights, right? We the people. These things are important. This is a new dawn. This is really the dawn of the information age, and it's the dawn of nanotechnology. These things are, in history, this is a time that you live in. You live in a period of history, and you should appreciate that somebody has to pick up the banner, like the flag, and they have to say that, science is it. And you guys can do things like you can cure cancer in your lifetime. So you have to have, this is an important summer for you guys, period. This isn't fooling around, and you can fool around, but you're going to miss it. And it'd be hell to talk to Da Vinci or something, right? You guys have that ability, or to be that man. So that's crazy. So as you can see, the mean free path can establish the size of a tool. The mean free path, which is a statistical number, mean free path, is important in many applications for many reasons, but the importance is clear with the evaporator example. Many nanoscale products are dependent on vacuum levels, typically at 10 to the minus 6 torr. This is a good estimate, and devices like lasers need deeper vacuum, maybe at 10 to the minus 9 torr, but there might be an exception. This vacuum is also important for characterization, and it's used for many reasons. Does everybody see that? It's not just used in nanotechnology. It's used in heavy industry. There's not a hospital that doesn't have many vacuum pumps in it, period. And it's not necessarily for nanotechnology. It might be for other applications, right? So there's vacuum pumps in dentist office. There's vacuum pumps everywhere, right? So vacuum and the concept of vacuum is tremendously important. So the next lesson, what we're going to go do is, this was a third of what we're going to talk, or half of what we're going to talk about today. And what we're going to do is look a little bit at pumps and gauges from this point, like the hardware. Does that make sense? So I wanted to do that. So we're looking at things like, let me go back in the slides. This is that mean free path, right? So you have to understand what a torr is. And that was that poor drawing that I did. Remember, that really was terrible when I had that pen. Actually, it worked out better than I thought it would. But, this is what we're looking at here today. And, just in what I told you was a tremendous amount of material. Does everybody see that? This was really fast pitch, but this is what, you have to be able to get as an engineer. And this is really important and kind of cool. So I think on your end is Pat, right? Pat, are you around? So I'll ask to talk to Pat now, I guess, while I drink my water.
I'm here.
So Pat, what I wanted to do, because these kids are kids, I saw them eating lunch. You see me drinking water. You can't see me because I'm in my stop share thing. So, hey, Pat, here I am drinking all this water. Here's all your students drinking water and stuff. What do we need to do? We need to take a bathroom break. Does everybody see that? So that's true. And we need to take a break just to stretch our legs. So that was a big chapter. We just reviewed, like, the question is, what is vacuum? Does everybody see that? What is vacuum? So I answered that question for you, and I gave you some sense of this is impressed on vacuum tools. And then I told you explicitly, without vacuum, we don't have like modern technology and sensors and Best Buy, right? Best Buy doesn't exist because 90% of what they sell is made with nanotechnology, right? And it impacts car tires and paint and all these other things. So vacuum is an important part of this construct. And I wanted to get that message apart. So from today, I think that was a success. Just to get that across, I think it was worth my time. I was proud to be your speaker today for that. But what I wanted to do is continue, but I wanted to take a short break because I got to get rid of this water, and then I'll allow you a short break. So how about what do you think, Pat? 10 minutes? Is that good? Okay, so let's meet back in 10 minutes, okay? So we'll